Okay, so in 7.2, let's recap what we did before break. In 7.1, okay, we were talking about using the z-table to build a confidence interval around a mean. Now this was done if we were going to take a sample of your guys' height and want to compare that to the school district or the high schools around the state. Say, look, we think the average height of a high school student is 5'5", okay? And we said that's the average. Well, how likely is it that the average here in Kimberly is the average across the state? It's not realistic that it's a perfect average. So we create these confidence intervals or bubbles around that guess or that estimation. And then we would say we're 95 or 90 or 99% confident based on the size of the bubble we created. The bigger the bubble, the more confidence we have. Okay, because if you have a giant bubble that's 3 feet wide for height, you should be very confident that the average is actually in that bubble. Okay? But we did that with a specific assumption. We had to know the population standard deviation. We had to know sigma. But what happens when we don't know sigma? Because if I take a sample here, I personally don't know anything about the population mean or standard deviation of heights of high school students. I don't have that data. So if I did a sample here, I would have to acknowledge that I don't know the population parameters. I'm going to be working off of all sample data. So in 7.2, we start to work on doing the confidence interval, but we don't have the population standard deviation. So when sigma is unknown, we're going to use the sample standard deviation, S, but it's going to change our process just a little bit. Okay? So when we're using S to, or the sample standard deviation, S, we're going to use what's called a t-distribution. There's going to be some characteristics of t-distribution we need to talk about. So again, if you know the population versus the sample, there's going to be a decision. And later on, as we do the end of this chapter, we're going to have to make a decision every problem. Are we talking about a population standard deviation or a sample standard deviation? Because it will change our process. This is what the t-distribution basically looks like. It's a set of curves. It's not one curve like the normal curve. It's a family of curves. And as you get n, the number of data points in your sample, as that increases, it starts to bend to fit and better fit the z distribution. So the bigger the n, the closer we're going to look to the standard bell curve. All right. Here's some characteristics, and there's some things that are very in line with the normal distribution, and there's some things that are different. So some things that are the same or similar, okay, to a normal distribution. It is a bell shape. Okay. It is symmetric about the mean. So right in the middle of that bell is the mean. The mean, median, mode are all equal to 0. So we put 0 right in the middle. We got negatives to the left, positives to the right. And the curve never actually touches the x-axis. You know, it gets really flat on the edges, and we think it's going to touch the axis. Never actually does. Mathematically, it's like an asymptote. It just approaches it. There are some differences, however. Okay? When we deal with the t-distribution, the variance, okay, which would be s squared, okay? So we talk about variance, we're talking about s squared. The variance is greater than 1. Okay? So that's one thing that we're going to claim right up front. Next, it's not a single curve. It's based on a family of curves. And those family of curves get more like the normal distribution as the sample size goes up. We're going to talk about that family of curves as being defined by what are called degrees of freedom, which we'll talk more about what a degree of freedom is. And 3, the sample size increases, the t-distribution will get closer to the normal distribution. The bigger the sample, the better. So could I say let's do a sample of 1,000 people? Sure. It's going to take a lot of work to do that though. And so the question is how perfect do I need this to be? The less I do, the less people I sample, the easier it is to sample, but the less the graph fits the normal distribution. So we like big sample sizes. All right. one of the definitions that we're going to have to clearly understand is what's called the degree of freedom. The degrees of freedom is the number of values that are free to vary after a sample statistic has been computed. So for instance, if I've got 10 data points, and I know that the sample has, so I've got 10 data points, and the sample has a mean of 3.5. Once I've figured out that that sample is 3.5, of those 10, 9 of them can vary around the other one, around that mean. So the degrees of freedom is always one less than your sample size, okay? Because we have to lock one value in place. Then the others can vary around that value. And so when you're being asked to pick the degrees of freedom, all you have to do is take your sample size and take one away. Okay? So it's a pretty easy calculation, but that's going to determine which set of values we use. We need to learn how to use that table that you have in front of you. Okay, so we're going to try to do these three calculations, okay, to build confidence intervals. Okay, this 90%, 95%, and 99% are confidence intervals. And these are our sample size and values. Okay? So you guys have that page out in front of you. Get your table out. Let's look at the table together. Pull that up. T-table. Your T-table should look something like this. Okay? A couple things I want to point out. Okay? You could do a one-tail or a two-tail test. If you guys remember from the Z-table, when we do a confidence interval of 90%, that means there's 5% on the left, 5% on the right that are being cut out. Those 5%, okay, would be equal to like 0.05 on each side. But on a two-tail test, you can see one tail, 0.05 in one tail, 0.10 if you're talking about both tails, because it's half and half, right? If you were to look straight down below that, that 10% on the two tails total equates to a 90% confidence level. Today, as we work through these, you're going to live primarily on this confidence level chart. It's where you're going to be looking, okay? So you're going to look down here on this bottom level, looking for your confidence level to help determine where our chart's going to match up. So the first one you were asked to find was 90th percent confidence with when the sample size is 18. Okay? So if the sample size, if n is 18, then when I go to my degrees of freedom over here on the left column, it says df, degrees of freedom, I want to find what value for my df. 17. It's the sample size minus 1. So there's 17. And what confidence level did I want for that first one? 90%. So my t-score, not z-score, but t-score, okay, would be 1.740 for 90% when I want 18 values in my sample size. Second one you guys had, I think it was 95%. But what was n equal to? 46. Now this is one of the downfalls to having a table. We don't want the table to be literally a mile long, so we have to have gaps as we get bigger. And so as we get more and more data, it gets more like the normal curve, and so there's some flexibility in it. But the truth is we can't do everything up through 1,000 or 2,000 or 3,000. So the table is condensed. Whenever this happens, we do our n minus 1, which would be 45, and we look for the next biggest. We can't do 45. It's got to be less than that. We'll never go over 45. We're going to look for the next biggest number besides 45. And that puts me at 40. It might feel like that's an aggressive adjustment, but it's the only adjustment we can make when we're using a chart. We will learn how to use our calculator to help in this process. Okay. But if I use 40 at 95% confidence, 2.021. Okay? And this is part of the process that you'll use to start your homework today. You're just reading the table, finding the correct t-value, so we can make calculations from here. All right, and what's the last one? What was n? Is it 82? Okay. Minus 1 would be 81. I don't see 81 on my chart, but I do have 80. Okay. And what was the confidence level we wanted? 99. Should be at 2.639. Are there any questions about how to read this chart, read this table? That confidence level on the bottom kind of sets where we're looking, and then we go to find this t-value. Now, because a t-chart is symmetric, this value is both negative and positive. On the left it would be negative, on the right it would be positive. Okay? Let's go back to our notes and see if we can make sense of the formula that's structured and how this works. This formula that you have on your page tells us that the mean, okay, the population mean, is going to be between these two values. The plus or minus produces two values. When we do the plus, it's the right boundary. When we do the minus, it's the left boundary. Okay? So we're going to create those two values that we're going to say the mean lives somewhere between these with, 95 or 99% confidence. Like with the z-distribution, if alpha is 0.05, meaning we want 95% confidence, there'd be 2.5 on each tail that we exclude. Okay? We create 95% confidence in the middle. Right? To calculate the equation, what these two values are, our boundaries for our confidence interval, well, I want to talk about how this is different than 7.1 and how it's really the same. If we were to go back to 7.1 and look at the formula, when sigma is known, okay, it would be x bar plus or minus z of alpha over 2 times the standard deviation over the square root of n. If you look at this formula versus the formula we're using today, the difference is we're using s instead of sigma, and we're using t instead of z. We're using a different distribution, but essentially it's the same calculation that we have to make. So there's nothing new in that mathematically. It's just a matter of which data do we reference. Okay? Let's take a look at an example of this and see if we can use our chart and be effective with it. All right. 10 randomly selected people were asked how long they slept at night. The mean time was 7.1 hours, and the standard deviation was 0.78 hours. Find the 95% confidence interval of the mean time. Assume the variable is normally distributed. A couple things. We did this yesterday in the other stats class, and we just did a rough estimate of people's average sleep time. I'll give people a chance to say, hey, how many of you think 7 hours, how many of you think 8, how many think 6, and so on. They did it with about 6.9. So it's not far off in terms of, we did a sample, same idea. What do you guys think? Do you think 7 hours is a fair approximation of the average number of hours that a high school kid would sleep? Might be a little low, maybe a little high for some of you. But somewhere in that window. You're always told 8 to 10 hours of sleep. I don't know if you've heard that number. Is a good number, especially if you're an athlete. Okay, anyway, we talk about this track, and kids don't always listen to me, but talk about it. That your rest after a workout is just as important, maybe more important than the actual workout. Oftentimes the work you do resting and sleeping and eating and nutrition is going to make a huge impact, whereas you might have run really good today, but that's going to fade if you don't have the appropriate rest with it. So anyway, back to this. So we want to be able to create this value. Since sigma is unknown, we use s to replace it. So the t-distribution gets used. Now, I'm going to tell you, they've already given us the t-value, but let's look at our chart for just a second. If there's 10 people sampled, right, we've got a sample of 10, our degrees of freedom would be 9, and we want 95% confidence. So if you look at your chart right now, you should be able to find the 2.262 off of that chart. Okay. So with that data and that t-value, we should be able to fill in our formula, which remember, looks something like x bar, our sample mean, plus or minus t of alpha over 2 times s over the square root of n, our sample size. So if we calculate this, the x bar is 7.1 plus or minus. The t of alpha over 2 that we got from the chart is the 2.262. The plus or minus gives us the left side and the right side, gives us those two boundaries. Okay? Times the standard deviation, that's a sample standard deviation, 0.78, over the square root of how big is our sample? 10. Clearly there's an addition version of this and a subtraction version of this. We're going to need to do both. So if one of you has got your calculator handy, can evaluate the plus side and one of you can evaluate the minus side, let's get those two values calculated so we can create our boundaries around the mean. When you think you've got it, if you'll let me know. I know it's 6 point something and like 7.6, so it's 6.5?
6.54.
6.54, we'll go there. And on the right, 7.66. So this sample that we took of 10 people, okay, had a mean of 7.1. That might not be the average of the population. Probably not the population mean. But we are 95% confident that whoever we were sampling from, that population is between 6.5 and 7.6 hours of sleep a night. Okay? And so decisions about, do we need to try and increase the amount that these people sleep? Is it enough and we're good? You know, do you do a health campaign to increase discussions about getting appropriate sleep at night? Well, is this a good enough number or not? So these confidence intervals are built that way. That being said, we know we didn't do the z-score tables, the confidence intervals from the z-table on paper and pencil the whole time. We learned how to use our calculator to do it. The same thing's going to happen with this t-interval. Okay? We're going to go ahead and learn how to use our calculator to do it. The notes for both z and t, the notes for both z and t are here, okay? The steps that you go through. But let's do this exact same problem, but we'll do it in our calculator and see if the table of the interval changes at all. So I come to my main page of my calculator, okay? And first thing I want to do is to press stat, because this is where my tests live. Okay? So we're going to slide over to our tests. We are looking for an interval right now. Okay? And we are using a t interval instead of a z interval because we're using the t distribution, because we do not have the population standard deviation. I believe it's option 8 for you guys, right? We'll select option 8. There are two versions of this. There's the data version, which requires you to put in a series of data values into L1 before you start. Did they give us a bunch of data on this question, or did they give us statistics about the data? They gave us statistics about the data, so I'm going to do the statistics side. What was the mean, or the x bar? 7.1. The SX, the sample standard deviation, was 0.78. The number of data values was 10. Notice, it doesn't ask me for degrees of freedom. The calculator has that built into its program. Okay? And what confidence level did I want? Was it 95? It was 95, so 0.95 is going to work there. I press enter to calculate. Okay? Up at the top left, I've got, at the very top of the screen, 6.542 and 7.658. Is that pretty close to what we had? Absolutely. So we can use that, okay, tool to help us build these confidence intervals. Any questions? Okay. Time's yours. I'll help you as much as I can. But get into the homework and we'll go from there. The first couple, 2 or 3